recorded 3 videos in a row, but changed my hair each time, so it's like it was 3 different days. Okay, I used to do this activity in person, and it was one of my favorite things to do, but it took, I'm not even joking, like 80 to 90 minutes just to do the activity. So it would be 2 class periods of just doing the activity, and then we could talk about it, and it was a lot. Luckily, there's an applet that will cut down on that time, and it'll actually make it hopefully more meaningful for you. So we have to get this applet set up, and there's a lot of steps, so let's set it up together and then I'll let you go off on your own. So you're going to click on the applet here, and then this is what it looks like. We are going to do the penny example, so pennies here, you're going to check that box, and then make the variable age. So we're not looking at the year the penny was made, we're looking at how old the penny is. So if it was made in 2020, it would be 0 years old. If it was made in 2019, it'd be 1 year old, etc. Oh, actually, never mind. I think this is based on the year 1999, because it says a penny made in 1995 is 4 years old. Okay, we're gonna do this activity like it's 1999. So here's our population of pennies. This distribution is clearly right skewed, and this is what the true population of pennies would look like. If I asked you, like, go out into your life and get a collection of like 100 pennies, most of the ones you find would be new, and you'd only get a couple that are really old. So we have a very clear right skew in our population. All right, you can see that the population size is 1,000 pennies, which is a lot. We're going to take some samples of pennies. So click on Show Sampling Options. What we want is 100 samples of size 1. I know that samples of size 1, not really a sample, but we're going to go with this. Click Draw Samples. Let me just show you around all the different things on the screen, and then I'll let you work on your own. This shows you that most recent sample. So it took 100. This is showing you the most recent. In this sample of 1, you got a penny that was 36 years old. This shows the most recent sample in a graph. It's a very interesting graph. There's 1 point. And then this shows all 100 samples, and it actually highlights the most recent one. So each of these boxes represents one of these samples of size 1. So you can see most of the time the sample of size 1 had a penny that was, what, 2 years old? Yeah, 2 or 3. You can click through them if you want. A couple times you got a sample that had 1 penny that was very old, but mostly it was around 2 or 3 years old. Now if you go back to the notes, it says for each one of these scenarios you're sketching the histogram. So that was sample size 1. You're just going to do a quick sketch of what that looks like. And then I want you to do the same thing with n being 5, 10, and 25. So all you have to do is change the sample size. Do 100 samples for each one. Just change the sample size. Once you've done that, you can answer questions 2 and 3, and then hit play, and we will recap all of this together, and I'll show you a picture of what the pennies actually looked like in person. So this is the product of doing this activity in person. I had this big bag of pennies, and then people would have to come up and take samples of size 5, and like every student had to do, I think it was 5 or 6, and then everyone had to do 5 or 6 samples of size 10, and then 5 or 6 samples of size 25, which is why it took all day. And then we would take all the pennies and lay them out into the population distribution. So this table permanently had that piece of tape on it that listed all the ages, and every year the other statistics teacher and myself would use it for like 1 week, and then we'd put it in the back of the room and not use it again until the next year. What I like about this is how crystal clear and shiny the pennies are all the way on the left, and then look how gross they get by the end. They're just disgusting. So anyway, it was a huge pain, and pennies are gross and they smell bad. Like my whole classroom would smell like gross pennies. And can you imagine doing this activity in 2020, like everyone touching the same pennies? So here's what mine looked like when I did it. When we're looking at how the shape changes as n increases, the shape is getting less varied and more normal the higher up we go. So with sample sizes of 1, our range went from 0 to 40-ish. And by the time we get to 25, our range is only from 8 to 16. Now you can't really tell that because the scale has changed each time here. A flaw with the applet. But if we pay attention to the scale on the bottom, we can see that we went from a range of 40 to a range of about 8. So that's a big improvement. We can also see that the shape is much more normal. In fact, there's a button here where you can overlay the normal distribution. So here I have a sample of size 30. You can see it's pretty normal. I'm just going to keep upping that for you. 40 pretty normal, 50 pretty normal. Let's go 90. Actually not as good as I expected. And now let's compare this final distribution of sample size 25 to the original population distribution. Remember, the original population was extremely right skewed. Like, there's no arguing that this is normal. It's not even close. But look at this distribution. It's so close to being normal. So the population was extremely right skewed, but the sampling distribution when n equaled 25 was approximately normal, which is pretty cool. And it turns out that's always true. This is called the Central Limit Theorem, which you can abbreviate as CLT. When the sample size is large enough, the sampling distribution will be approximately normal no matter what the population looked like. Now, large enough, we're going to just say greater than or equal to 30. I know it's kind of arbitrary, but we're just going to use that as a general rule. So if in the last video you were like, what do I do when the population isn't normal? Here's your answer. As long as the sample size is greater than or equal to 30, you can assume that the sampling distribution is approximately normal, and you can use all those normal calculations that we learned back in Unit 1. We've done a lot. We've done sample proportions and sample means. So what I'd like you to do is just kind of process everything we've done so far and condense it into these two boxes. Write down how to calculate the mean and standard deviation, what you need to use in order to find the standard deviation, and then how to know that the sampling distribution is normal. You can look back at old notes or old videos if you need to. This is everything from the entire unit in two boxes. No pressure. Ready, go. Okay, so the formulas, I'm taking those right from the formula sheet. For both proportions and means, you have to check the 10% rule in order to use the equation for standard deviation. For proportions, the sampling distribution of p hat is approximately normal if np and n1 minus p are greater than or equal to 10. For means, you've got two different things. Either the population distribution is normal, or the sample size is large enough that you can use the CLT. Now, if you are using the CLT, you should say, by the CLT, somewhere in your explanation. The next couple problems are mixed. They're both proportions and means. So what I'd like you to do is try all of the problems on the next page. I'm going to hope that this lawnmower stops by the time I'm done with them, and then we'll go over the answers together. So pause the video, do as much as you can on your own, and then we will recap. The lawnmower is still going. I'm done waiting. Okay, so I'm not going to read this problem to you because you've already done it. So p hat, we're dealing with proportions. So I'm using the mean of the sampling distribution of p hat and the standard deviation of the sampling distribution of p hat to get 0.74 and 0.044. We need to assume that there are more than 1,000 families in the district. That's definitely true of my district. If it's not for yours, it's okay to just say, we'll assume that this is true. For normal, when we're dealing with proportions, we have to check NP and N1 minus P. Here that's 74 and 26. Those are both greater than or equal to 10, so we're good. Now we get to the actual probability question. What's the probability of getting a sample of families where p hat is less than 76.9%? So I started with a picture. Here's the sampling distribution of p hat. The mean is 0.74. 0.769 is quite a bit above the mean, and we want the probability of getting something less than that p hat. So picture first, then I wrote it out in symbols. The probability that p hat is less than 0.769. Then converted to a z-score, used norm CDF. The probability of that happening is 74%. So there's a pretty good chance that they get a p hat that's less than 76.9. Okay, this is a leftover problem. There's one year I taught statistics first period, and everyone was just rolling in late every day, and so I made a really passive-aggressive test question about the number of tardies in first period. No one commented on it, so they were either really mad or they were so tired in first period that they didn't even notice that I was throwing shade. Okay, so this first one, I am picking a random senior from a list of all seniors. So this is not about a mean, this is one randomly selected person from a population. However, our population is not normal. We are told it's not normal, which means we can't do this. You might start by doing a picture, you might even write this out, you might even start doing norm CDF. At some point you have to recognize, wait a second, this wasn't a normal distribution. This isn't what the population looks like. It's either right skewed or left skewed. So we can't do this calculation because the population distribution isn't normal. So yeah, sometimes in statistics you have a problem that you have to write I can't do this. It's kind of fun. Okay, so now I take a sample of 35 seniors, yours is hopefully fixed from the list, and call down to attendance. So now I'm dealing with a sample. Instead of one randomly selected senior, it's a sample of 35 seniors. And instead of looking at one person's number of tardies, I'm looking at the mean number of tardies in the sample. Okay, so the mean and standard deviation of the sampling distribution of X bar is what that should probably say. Just using the formulas from the formula sheet, we have to assume there are more than 350 students, I guess that should say seniors, at the school. Okay, let's get right into the probability. So here's our sampling distribution of, there we go, of X bar. Mean was 7. Probability that we have 8 or more tardies as our X bar. So 8 is over here, and or more means we're shading to the right. In symbols, we are finding the probability that X bar is greater than 8. Z-score, norm, CDF. There's only a 1.66% chance that the average number of tardies in my sample is more than 8. Pretty low chances. Now we are supposed to explain why we could do that calculation. Only in statistics does your teacher say, why could you do that? It's a valid question. We were able to do this. The sampling distribution of X bar is approximately normal by the CLT because the sample size, which is 35, is greater than 30. More commonly, you'll see it written as, we can assume the sampling distribution is normal by the CLT, and then in parentheses you should probably say, n is greater than 30. This is the reality of doing problems from here on out. It's not going to be like, now we're doing sample proportions, now we're doing sample means. It's just going to give you some information and you have to figure out if the problem is asking you about proportions or means. So pay close attention to the wording of the problems, circle things as you read, jot down mu, standard deviation, normal as you read, and then as always, make a picture and write out what you're trying to find in symbols. I can't tell you how many times it saves you from making a mistake if you just write X. If writing X versus X bar can help you remember if you're dealing with the population or the sampling distribution. And overall, I would say don't try to memorize anything in this unit. Just think through things logically. Am I dealing with the whole population? Am I looking at a sample? Am I looking at a proportion or a mean? You can think through this process without memorizing. And in the end, that will take you so much farther in future units if you're able to think through this logically as opposed to just memorizing when to do this or when to do that. So yeah, I guess I'm saying use your brain. It is capable of more than you think it is capable of. So use it.